Bismillahirrahmanirrahim. My dear students, dear followers, this is an exercise about accumulation points, isolated points of on R. Usual topology. So here we are in R, and this topology is related to absolute value. Let us start by determining the accumulations point and isolated point if they exist. First of all, definition. Here we have a definition. Let a set A be a part of R point A from A, and this is here very important. So a point from A is said to be an isolated point of A if and only if this is a definition by characterization there exists a neighbor V from V such that V minus A intersection A equal empty set. This is the definition of an isolated point. Isolated point. Second definition. In the same condition, let A be a part of R, a point A from not from R necessarily, but from R, not from A necessarily, but from R. So this is the second important remark. Is said to be an accumulation point, of A for sure, and an isolated point of A. If and only if for all neighbor of V of A, or the neighbors of, this is neighbors, V from voisinage in French, neighbors of A, for all the neighbors, one has V without A, intersection A, this is different of phi. This means that there exists at least another point other than A such that the intersection is non-empty. This is the definitions of isolated point and accumulation point. What we can retain here, the point is from A, and there exists a neighbor, and here the point is from R, not necessarily from A, and for all neighbor. Let us draw this set. We suppose that this is the line, the real line. And find the isolated and accumulation point of A, and belongs to A and index 0. This means 0 is included. This is 0, so n equal 0, 2 over 3. So 2 over 3. We suppose that 2 over 3 is this point. When n goes to plus infinity, it goes to 0. N equal 1, so 1/2. 2 over 1 plus 3, so we have 2 over 3. We have here 1/2. N equal 2, we have 2 over 5. We have 2 over 5, and so on. And so on. This is 0. We can suppose that this point is for a given n0 plus 3, for n0 which belongs to n. Yeah. So please retain these definitions to understand the upcoming explanation, facilitated explanation I hope. Now, this is necessary to keep these definitions in your mind. Once again, we suppose that this is the real line. This is 0. This is 1. So here for n equals 0, we have 2 over 3. So here 2 over 3. For n equal 1, we have 1/2. And so on. And let us suppose that here, this point, so this points and this point and this point. This point for n0, for n0 from n, for n index 0 from n, any given natural number greater than 1, big enough. Here we have 2 over n0 plus 3, and here this is 2 over n0 minus 1 plus 3, which means n0 plus 2. And here we replace n0 by n0 minus 1, and here this is less than, this is 2 over n0 plus 1 plus 3 means plus 4. So this is the points. Let us discuss in mathematics. We guess and then we prove. So we guess, we suspect that some results are true, and then we prove what our guess. Here we guess that the isolated point are 1, 2 over 3, 1 over 2, 2 over n, 0 plus 2, all this point. So for all the points from A, they are isolated point. Why? So let n0 be a real number, a natural number from n0, then 2 over n0 plus 3 is an isolated point. Why? We come here, this is the point. We calculate the length, the distance here between this point and the next point. This distance will be called epsilon 1, and this distance is epsilon 2. Epsilon 1 is equal to 2 over n0 plus 2 minus this point 2 over n0 plus 3. And this gives us, so here we have n0 plus 2 times n0 plus 3. Here we have 2 n0 minus 2 n0, and we have 6 minus 4, so we have 2, which is positive, strictly positive. And epsilon 2, this one, epsilon 2, is equal to this point, which is 2 over n0 plus 3. Let us write it here. And epsilon 2 equal 2 over n0 plus 3, 2 over n0 plus 3 minus 2 over n0 plus 4, this point. And this gives us 8, so we have 2, and here we have n0 plus 3 times n0 plus 4. What we remark that obviously, without doing any calculation, we remark that epsilon 2 is less than epsilon 1. So, the neighbor that we need, without loss of generality, we can consider all the neighbors under this form. The neighbor of this point, which is the neighbor of 1, the neighbor of 2 over n0 plus 3, and 0 plus 3, we can consider this neighbor as what? The neighbor will be this one. We take the minimum between epsilon 1 and epsilon 2, which is epsilon 2, then we divide epsilon 2 on 2 parts, and we take this open neighbor. This is a neighbor, but at the same time is open, and I said without loss of generality we can take this. We get here what? We get here 2 over n0 plus 3 minus epsilon 2 over 2, and 2 over n0 plus 3 plus epsilon 2 over 2. We find a neighbor, this neighbor, such that this neighbor, if we take off the point 2 over n0 plus 3, the intersection with A is an empty set, which means that any single point of this set is an isolated point. Let me do it completely. We take this neighbor, there is this neighbor, so we find a neighbor. This is the question. We find the neighbor, and what we have V with respect to this point of the set minus the point intersection A. This is, so we have this neighbor, we take off this point and we make the intersection with A. Here there is no points of A common point with this neighbor, so this is equal to empty set. This implies in a very simple way that any single point of A is an isolated point. We're done with isolated point. There is no other isolated point. Why? Because basically in the definition we said that an isolated point should be a point of A. And since all the points of A are isolated points, there are all what we need about isolated point. Let us move to accumulation point. For the accumulation point, we have three kinds of points. We have this kind, we have the points which are greater than 2 over this point, which are greater than the supreme or the maximum, and we have the point which are less than the infimum, and we have the points which are here between the points of the sets. A actually is this point, this point, this point, and etc. This point and this point. This is A. Between the points, the elements of A, these points aren't elements of A. And greater than the maximum of A isn't points of A. And less than the infimum of A aren't points of A. So, this is two simple cases, basically. A point from here, denoted A, cannot be an accumulation point. Why? Because if we consider a point here which is strictly greater than 2 over 3, we consider epsilon, which is equal to A, minus 2 over 3, which is greater than 0. And we take here the interval, this interval intersection A is empty set. And to be an accumulation point, we need all the neighbors intersection with A without the point A, intersection with capital A without this point, we take off, should be different of empty set. For this interval, we have A minus epsilon over 2, this epsilon, A plus epsilon over 2, minus A, intersection A, this is empty set. So, this point cannot be an accumulation point. Let us move to this side. Here, A means negative. And once again here, epsilon equals 0 minus this distance from this side, minus epsilon, minus A. And since A is negative, this means that this is positive. And once again, we can find this interval such that the intersection, we take A minus epsilon over 2, A plus epsilon over 2. If we take off A minus A, intersection A, this is an empty set, so this point can never be an accumulation point for A. what do we have next? So here, retain that, we proved that all the points here cannot be accumulation point and all the points here cannot accumulation points. The last case, between these points, in blue color. If we suppose that this point is 2 over n0 plus 3, this one as below 2 over n0 minus 1 cell plus 2, and this point is 2 over n0 plus 4. If we take a point here, we calculate this distance and this distance. We calculate this distance and this distance. I mean, we calculate epsilon 1, which is this point 2 over n0 plus 2 minus I, and epsilon 2, this distance, I minus this point mean 2 over n0 plus 3. We compare between them. We suppose that, for example, epsilon 1 is smaller. If epsilon 1 is the minimum between these two, we take this interval, such that here we take v, which is I, minus the minimum between them, the minimum between epsilon 1, epsilon 2 divided by 2, and I plus the minimum between epsilon 1, epsilon 2, and the intersection of this neighbor without I, which is basically an element from R and not from capital I. The intersection is an empty set, so any given point of these points cannot be an accumulation point. The last special point is A equals 0. We will prove that 0 is an accumulation point. Why? Because 0 is an accumulation, the unique accumulation point of A. Why? Because for all V, which is the neighbor of 0, V without loss of generality takes this form. For all neighbor, take this form. This means for all epsilon greater than 0. So for all V neighbor of 0 is equivalent, in this case, for all epsilon 0, the neighbor, this neighbor, describes without any loss of informations that we are in the general case, this one. V minus 0, this is equal minus epsilon 0, union 0, epsilon. And if we take V minus 0 intersection A, this turns to 0 epsilon intersection A. And can we find, does n0 belongs to n0 such that what? Such that the element, this element, these two be in all cases different of 5. So n0 should exist here, such that what? Such that 2 over n0 plus 3 is less than epsilon and greater than 0. Is this possible? The answer is sure true. Why? Archimedean property. If you remember the Archimedean property. Even if you don't remember the Archimedean property, here this is positive and all this is positive, which implies that n0 plus 3 is greater than 2 over epsilon. So n0 greater than 2 over epsilon minus 3, and here we have cases to discuss. Anyway, the n0 can exist. It is sufficient to take the integer part of 2 over epsilon minus 3 plus 1, and this natural number verifies this double inequality, which confirms that 0 is an accumulation point. This is all. I hope that this video will be useful, beneficial for you. Thank you very much, my dear students. See you next time, inshallah.